So welcome everyone. Today, in today's seminar, we'll listen to Twesh Upadhyaya. He is a PhD student in University of Maryland in Nicole Younger Halpern's group, my favorite quantum thermodynamics expert. He has a few papers on quantum key distribution, but today he's going to talk about his one of his latest works, how non-abelian transports change our understanding of entropy. So this stage is yours.
Great. Thanks, Benoit, for the introduction, and to CQIQC for being able here to give this seminar. So today I want to talk about how a very quantum effect of non-abelianity, non-commutation impacts transport and specifically entropy production. And this is work with my collaborators at the University of Maryland, Billy Brash, Gabriel Landy, and Nicole Younger Halpern. So the setup we consider is something very ubiquitous across physics, across many different examples, which is two systems that are exchanging some quantity that's conserved in total, but can be exchanged between the two systems. And sort of an analogy with electric charge, we call these quantities charges. So our systems A and B exchanging some quantity. It can be, for example, energy. So an ice cube melting in water. It could also be the particles of water that are being exchanged as the ice cube melts. And here's a very simple classical example, but for a more quantum example, we could think about two qubits exchanging spin in some way where the total x, y, and z spin is conserved between the two qubits, but it's shuttled back and forth by some interaction. In these kinds of scenarios, we often assume the systems start in thermal states. So here, like a Gibbs state. And of course, when the two systems are at different temperatures, we get some non-trivial dynamics. And ice cubes melt in water, they don't refreeze it. So similar way, these processes are associated with some entropy production, some irreversibility. And this has been pretty well studied for classical systems, as well as quantum systems where all of these charges, these conserved quantities, commute with one another. The key question we ask is, what happens when these charges are non-commuting? And there's precedence in thermodynamics to believe that this in general leads to new phenomena. So when it comes to even figuring out what the thermal equilibrium state is, it's been shown that non-commutation invalidates some of the existing derivations, and so new tools are needed to prove what state a system thermalizes to. For the eigenstate thermalization hypothesis, which answers the question of how isolated quantum systems, or at least small parts of them, can appear to thermalize even though they're undergoing reversible unitary evolution. Again, the existence of non-conserved symmetry, non-commuting symmetries, which show up in the Hamiltonian, or these non-commuting charges, has been shown to lead to larger corrections. And finally, people have studied entropy production in just the linear response regime, and there again showed that non-commuting charges actually reduce the entropy production. So for the rest of this talk, when I say the commuting case, I mean all of the charges commute in this sort of classical setup. And when I say non-commuting case, it means there's at least one pair of charges which fails to commute. So before getting into the meat of the talk, I want to kind of summarize what the main takeaway is. We start with the commuting case, where there's sort of these well-studied three different formulas for entropy production. And they all reflect the same definition. So they're just completely equivalent and interchangeable. We adapt the formula slightly to accommodate the non-commuting charges that we studied, this more quantum setup. And we find actually that these formula are no longer equal. So non-commutation drives the three formulas to be different. And each one highlights some interesting aspect about transport and what's going on in these underlying evolutions. So for the rest of this talk, I'll first introduce just some setup and background in a bit more detail, the system we're looking at. I'll then talk about what exactly do I mean by stochasticity and introduce this notion of quasi-probabilities. And finally, I'll briefly discuss our three definitions, which we dub charge, surprisal, and trajectory. Okay, so back to our setup, we have our two systems A and B, and the charges they're exchanging are going to be denoted by this Q alpha. And there's C such charges. So for example, if it was just energy being shuttled back and forth, C would just be 1, and our Q alpha would just be the Hamiltonian. The interaction that's going to mediate this transport is just going to be some unitary U acting jointly on both systems. And like I said, we'll assume the systems start in thermal states. But what exactly we mean by thermal states is a little bit different because we have more than one conserved quantity. So we're used to seeing an expression like this with just one term, which is just the inverse temperature and a Hamiltonian, and we recognize this as a Gibbs thermal state. And if we think back a little bit to something like the undergrad thermodynamics, we sometimes see grand canonical ensembles where we would have two terms. So we would have an inverse temperature weighting a Hamiltonian, and we would also have some temperatures and chemical potentials weighting the particle number operator. But in general, if we have many such conserved quantities, we can associate all of them to some inverse temperature and collect them all in the exponential with, of course, some normalization. Such a state is often called a generalized Gibbs ensemble. And specifically when we're looking at these Qs, these charges which may not commute, it's sometimes referred to as a non-abelian thermal state. So in the usual fashion, we start off with a tensor product of these thermal states. It evolves into the unitary to some final state. And in order to have a sensible notion of transport, we don't want charge to be created out of nowhere, only moved between the two systems. So we demand that our unitary that's driving this evolution should commute with the total amount of charge. So that doesn't change, it only gets moved between the two systems. And it's not super crucial, but just a little notation that we're going to see pop up later on. For each charge, we're going to think about its eigendecomposition. So it'll have some eigenvalues lambda and some eigenprojectors pi. But just simply, you can think about this for energy. These are just energies and then energy eigenvectors or energy eigenspaces. Okay. So far I've talked about two systems, a unitary evolution, but this is all sort of deterministic. There's no explicit randomness or stochasticity, but that stochasticity comes in when we think about measurement. So we're now trying to probe the systems, ask how much charge is actually being transported. So the sort of canonical example for how people study the transport is done in the very simple case where just energy is the only charge. We start by measuring the energy of the two systems, evolving them, and measuring the energy again. Pretty straightforward. And this goes by the name of the two-point measurement scheme, oft-cited in the literature. So if we think about the initial and final measurements, we basically get four different outcomes. And we can think about the system as having gone this two-step trajectory. So it started off, systems A and B both started off with some definite energies, and they ended up in some definite energy at the end. And this occurred with some probability, P. And now suppose we had more charges than just energy. You could consider generalizing this kind of scheme, measure all of the charges, evolve via the unitary, and then measure them all again. Well, you would just have a bunch more indices, but everything would otherwise be the same. And already you can see the notation starts to get a little messy. So just for simplicity, I'm going to write I1, I2, and so on. But that's just a way of wrapping up and not writing out A and B separately. So there's nothing sophisticated going on there. I'm just not writing out A and B. This is like a composite index for both systems. But there's a key problem that some of you may already be thinking about. When I say to measure all of these charges one after the other, I'm going to cause disturbances if the charges don't commute. So for example, if I measure in the X basis for a qubit, my subsequent measurement in, say, the Y basis is going to give me a different result because of the disturbing nature and the fact that these are non-commuting observables. So instead of using these strong measurements, what if we use weak measurements instead? Okay, well, what are weak measurements? First, let's just review what a strong measurement is. So in the lab, the way we actually implement a measurement is we take our system of interest and we couple it to some measurement apparatus. Let's say some interaction Hamiltonian, H int, and we let these two evolve together for some time. After which we sort of look at or collapse our measurement apparatus, we get a readout, and conditioned on that, we collapse the state of the system. A weak measurement is going to be something very similar, except we're not going to let the system and apparatus evolve for that long. So they won't become as correlated or as entangled. And on one hand, that means we disturb the system less, so there's less back action on the system, but also, of course, we learn less. There's a trade-off. And in the extreme limit of no interaction time at all, we would have no measurement, If we let it evolve for the full time, we have a strong measurement. So these weak measurements are kind of interpolating in one sense between no measurement and a strong measurement. We're very used to seeing in quantum mechanics probabilities with our POVMs or just with simple like projective measurements to describe the probabilities of various outcomes when we write down, when we do such an experiment. And it turns out, well, we could always describe, of course, any experiment using probabilities. But for these weak measurement experiments, there's an alternative description in terms of quasi-probabilities, which is very natural. Okay, so maybe I'm raising more questions than I'm answering, but what are these quasi-probabilities? Well, just like probabilities, they're a distribution, so over a set of indices or maybe a continuous phase space. And they satisfy most, but not all, of the axioms that a probability does. So for example, it may sum up to 1, but certain elements can be negative, or as we'll see, we'll study ones where they can even be complex valued. So with that in mind, let's go back to the stochastic description we talked about, where we measure a whole bunch of charges, evolve, and then measure them all again, and see how this might be updated to account for weak measurements instead of strong ones. So for strong measurements, we simply start off with our state rho. After the first measurement of charge 1, we just bracket it with the relevant projectors, do this all the way for the last charge. We then evolve, Before
you say you measure sequentially, the order matters.
Yeah. So one thing you'll see here is what I've written down is like a very specific ordering where I say, okay, you measure charge 1, 1, 2, 3, so on. But after the unit evolution, you're measuring the last charge first and then kind of reversing the order back to 1. That's intentional because we want to show that later on we're going to kind of propose definitions for entropy production, and we want them to satisfy some sanity checks. So like if there's no evolution, for example, there should be no entropy generated. And it's important to sort of fix this relative ordering in order to satisfy these sanity checks. So, right, we start with our state rho, do these measurements, evolve unitarily, and finally we do the final set of measurements. This is just kind of a straightforward, albeit a little elongated probability. For the quasi-probability corresponding to a weak measurement scheme, where we do all these measurements, but only weakly, it's going to look very, very similar, almost as if we actually just forgot to write down all these projectors at the end. Okay, so this thing looks a little bit new, but let's just do some sanity checks. When everything commutes, so all the charges commute with one another, and rho is, of course, this tensor product of thermal states, this quasi-probability just reduces to the regular probability. So it recovers what we know in the sort of classical or commuting case. And it has some other properties. It normalizes to 1. If we just sum over all the indices, we just get 1. And it recovers the correct marginals. So what do I mean by that? Let's say we summed over all of the indices except, say, I2. Here, when we sum over a projector, it just sums to identity because it's a POVM, and it just vanishes. In contrast, in the strong measurement scheme, when we sum over, say, all the projectors I1, we're left with a dephased state rho. So we lose all coherences in this I1 basis. So it has some nice properties that'll help us describe the flows of charges. But of course, as a consequence, it may take non-real values, and we'll have to work harder to put an interpretation to these negative and imaginary pieces. Just as before we thought of the system following a sort of discrete two-step trajectory weighted by some probability, loosely speaking, when we're describing the system, the stochastic description with these quasi-probabilities, we want to retain sort of a similar interpretation where, kind of like in a path integral formalism, the system is taking these different trajectories with potentially complex weights. And finally, before we introduce our definitions, let's just review what is this usual formula for entropy production in the classical case, and what are these 3 formulas which we generalize. So conventionally, we think in terms of these probabilities, and the entropy production is just a random variable over this distribution. it tells us on a particular trajectory how much entropy was produced. We are now going to generalize to think of random variables over a quasi probability, in keeping with our line of a stochastic description with these Kirkwood-Dirac distributions. And as I've mentioned, there's a single well-accepted definition, which we're then going to generalize. And the generalization is going to be accommodating quasi-probabilities instead of probabilities. So the definition in this two-point measurement scheme of the stochastic entropy production, the sort of commuting case, basically starts from this idea of a forward and a reverse protocol. The forward protocol is, as we've discussed, to prepare some state rho, measure the energies, evolve, and measure them again. In the reverse protocol, we prepare the same initial state, except our first measurement of energies, we actually assign the outcomes with indices f, like our final indices. We perform U dagger instead of U, or equivalently prepare some time reverse state, which has been evolved. And then we measure the energies again, but we assign these to the initial indices. The entropy production is defined as the log ratio of forward and reverse processes. And so sort of intuitively, we're used to this idea that the universe proceeds in the direction that spontaneously increases entropy. So if the forward direction is more likely than the reverse one, this is larger than 1, the log is positive, and this kind of checks out that there's a positive entropy production. And similarly, if the reverse direction was more likely, it would actually be negative entropy production. So we can simply plug in for these probabilities. There's the probability of our initial measurement, and then a transition probability, which we can just write with the unitary. So for the reverse process, I'm saying this is my outcome after measuring the initial state. I collapse to some energy eigenstate. I then evolve it and take the overlap with some final measurement I. But if you stare at this for a little bit, take some complex conjugates, these two terms actually cancel. And so we're just left with a log ratio involving measurements on the initial state. And remember, our initial state takes a very particular form. It's a tensor product of thermal states. So being careful with your signs, you can sort of see that it's going to come out to look like something like this. So for example, like the probability of this measurement on system A is going to look like e to the minus beta A EFA. Because it's in the denominator, it comes out with the opposite sign. And basically, I want to draw your attention to 3 steps in the simplification, which we're then going to look at generalizing. The first is this formula, where everything is just expressed in terms of inverse temperatures and eigenvalues of energy, but more generally of whatever charge we're considering. This step, where we're just interested in a measurement on the initial state, so there's no mention of the unitary dynamics. And the very top formula, which was sort of the starting point, which is the log ratio of a forward and a reverse process. So with that, we're now ready to introduce our 3 different formulas, or flavors, if you will, of stochastic entropy production. The charge, which really connects to entropy's role as an extensive thermodynamic variable. The surprisal definition, which really harks back to entropy's roots as an information theoretic measure of uncertainty. And finally, the trajectory definition, which connects to entropy's key role as a quantifier of irreversibility and its involvement in the notion of the arrow of time. So put up the first formula now for charge, and there's a lot of indices floating around. We don't have to worry too much about the details. The key point is, for every charge alpha, we have a term that looks exactly like what we saw on the previous slide. We have differences in eigenvalues weighted by inverse temperatures. For the surprisal definition, we have, again, something that looks very similar to what we saw on a previous slide. For some charge alpha, we do measurements of the initial state in that basis, and we take the log ratio of measurements with I and F indices, which is just like the second last line on the previous slide. And finally, for our third definition, this, if you recall, was the first formula on the previous slide, except instead of using a forward and reverse probability, we've actually used a forward and reverse quasi-probability. And these retain a very similar interpretation. So the forward one is the same one we've talked about. And we can kind of read this off as preparing rho, measuring charge 1, unitary evolution, and so on. The reverse, yeah.
Alpha and arbiter observable.
Yeah, here alpha is like a choice. And the reverse quasi-probability we can read off in much the same way. We prepare rho, perform the first measurement, but assign it to an outcome F1, evolve via U dagger because this U is hitting the rho on the right side, and again, perform all the measurements. So with that, I now want to talk just a little bit about our three definitions and kind of give a key takeaway from each one. Basically, by construction, the average of this charge definition closely resembles something we're used to seeing in classical thermodynamics. So what we get is a sum, again, for contribution from each charge, a difference of the inverse temperatures multiplied by the change in the charge. So this is basically saying how much, for example, energy flowed into system A. And it turns out that this formula can also be expressed as a relative entropy. And that tells us at a glance that this is something non-negative. So this relative entropy, or sometimes called Kullback-Leibler divergence, is always non-negative. And again, thinking back a little bit to undergrad thermodynamics, we're used to seeing this relation, sort of fundamental relation of thermodynamics, which tells us how differential changes in extensive quantities are related. And if we kind of stare at this a little bit, it's very similar to what we have here, in that this ds is related to a 1 over t dE, or a beta dE, and similar terms for every extensive quantity, so volume, particle number, or whatever the delta Q's are in your case. Except it's worth noting that the fundamental relation is only valid for infinitesimal changes. This formula holds arbitrarily far from equilibrium. The delta beta, delta Q do not necessarily have to be small. So sigma is a random variable, or quasi-random variable, because we're averaging. This average is against a quasi-probability. So beyond just looking at its first moment, we can also look at higher order moments. And one thing that's often studied in just classical stochastic thermodynamics is a fluctuation theorem. A fluctuation theorem is just the computation of, instead of the average of sigma, the average of e to the minus sigma. Now, why is that interesting? What does it mean? Well, conventionally, these fluctuation theorems read something like, and these can actually be thought of as a tighter statement than the second law of thermodynamics. So what do I mean by that? Well, when we're close to equilibrium, the second law tells us more or less something in equality. It says, okay, the entropy you've produced is close to zero or is equal to zero if you're in a reversible process. If we're very far from equilibrium, the second law just tells us, okay, there's some non-zero entropy production, but it doesn't tell us anything about how much non-zero entropy production. On the other hand, this statement on my fluctuation theorem or Jarzynski equality is valid arbitrarily far from equilibrium, and it's always an equality. And when I say it's stronger than the second law, I mean we can actually recover the second law from this using Jensen's inequality to recover that on average, the entropy production is larger than zero. So these fluctuation theorems are a powerful way to kind of encode information about moments of the entropy, stochastic entropy production beyond just the first. So what we do is compute an analogous quantity, except again, our averaging is with respect to a quasi-probability, not a probability. And we find that it has the 1 on the right-hand side that we've come to expect from the classical case, but there's two different kinds of quantum corrections. And the first one is from the thermal state itself having non-abelianity, in that the charges that comprise it may not commute. But what I really want to focus on is the second term, which is a correction from what we dub non-conserving trajectories. So what are these trajectories? Just consider some alpha, so some charge, and consider this equation for its eigenvalues. So we look at some I alpha and I alpha b, and we look at some FA and FB, and we ask, are these two quantities equal for some choice of indices? If they aren't, we say this corresponds, these indices, which remember just label our trajectories, correspond to a non-conserving trajectory in the sense that the charge sort of stochastically seems to be non-conserved. Now, normally we don't worry about these trajectories because in the commuting case, when all charges commute, this quasi-probability, again, reduces to just a probability, but it's zero on non-conserving trajectories. So they play no role. They don't show up in any of the calculations. They have no weight. However, in the non-commuting case, you can actually have non-zero weight on these kinds of trajectories. And in some ways, this is very reminiscent, again, of a path integral formalism. We're used to seeing classically forbidden trajectories that don't show up in a classical description and they play no role in calculation. But if you look at an electron going through a double slit experiment, this quantum object is actually able to explore all these previously forbidden paths, and that leads to some observable consequences. And in a very similar way, these non-conserving trajectories are accessible when you have non-commuting charges, and they lead to a correction to a fluctuation theorem. Some ways we can think of this as a violation of charge conservation at the stochastic level. But I want to emphasize that throughout all these derivations, it's still true that the unitary commutes with the total charge observable. This sort of says there's some fluctuations of this charge conservation stochastically, but when you look at the entire system, you don't see them. So there's kind of two notions of charge conservation I've talked about so far. Okay. Next for our surprisal definition. And here the key takeaway is found in the average. So this average looks pretty similar to what we saw before. There's a relative entropy showing up, except there's also a second relative entropy. And both of these don't just have the state rho in the second argument, but they have rho acted on by a quantum channel, which is just dephasing in the basis of charge alpha. And again, alpha was just some arbitrary choice for where we even defined the surprisal in. This is the same choice. So just quickly, does this recover what we're used to seeing? Well, when the initial state is diagonal, so when all charges commute, rho is going to have also commute with all of them because it's just the exponential. And if we dephased in that basis, we wouldn't change rho, so we could just ignore the dephasing. The relative entropy of rho with itself is just zero. And here we would be left with the relative entropy of rho f and rho, and that's exactly what we saw on the previous slide. So this simplifies back down to what we've seen before. But when rho has coherences, and these coherences are basically created by the non-commutation of charges, actually this term can be smaller than just the first term alone. And in fact, this entire term can be negative. And that's surprising because we started with a tensor product of thermal states. And typically we associate this with a process that'll increase entropy. But here we see that a very quantum effect of quantum coherence is, loosely speaking, playing the role of a resource to sort of reduce entropy production, sort of simulate a reversal of time's arrow. And certainly this is something we would want to investigate further, whether we can put this on firmer footing to really say these coherences can be used in some way to do some sort of work or reduce entropy production in some way. And finally, I'll talk about the trajectory definition. And here again, we'll look at the average, but just the imaginary part of the average. What we find is that this imaginary part actually signals contextuality, which is a very strong, rigorous notion of non-classicality. So what are these phi f and phi r that show up on the right-hand side? These are weak value phases. So without getting too much into the details, a weak value is a number we can get out and is very closely related, a number we can get out from an experiment, which is very closely related to the weak measurements I talked about earlier. But really, I think the easiest way to think about this term is geometrically. So we're used to entropy production telling us something about a difference between forward and reverse directions. So when a glass of water just sits on a table, nothing happens. There's also no entropy produced. We can't really tell, are we watching this glass of water? If you had a video of it played in forward or reverse, we could very easily recognize if we saw a mug, a shattered mug putting itself back together, that we were watching a video in reverse. Similarly, this entropy production is going to talk about a difference between forward and reverse processes, but in a little different way. So let's think, for example, about the block sphere, just a qubit. And imagine the forward protocols we've talked about with strong measurements. The qubit, just for simplicity's sake, starts on some pure state on the surface of the sphere. It moves to a different state, conditioned on getting some measurement outcome, some unitary evolution, another measurement, and we can just close up that path with a final geodesic. And ultimately, we subtend some area in the block sphere, and this area is a geometric phase. Similarly, we could start from our same initial state, but now run our reverse process, and the qubit would follow some different path on the block sphere and subtend potentially a different area. It's the difference of these two areas, or these two geometric phases, that is this entropy production. And so we see that in a similar way that classical entropy production captures a difference between forward and reverse processes, so too does this trajectory definition, just the difference is about the evolution in state space. And it's kind of neat, but basically the fluctuation theorem for this definition is simply equal to 1, kind of nice, very similar to, or exactly the same as the classical case. Okay, so to summarize, we started with these 3 formulas for stochastic entropy production, equal in the commuting case, but not equal in the non-commuting case, each of which tells us something interesting about the transport. So for the charge definition, we saw this idea of non-conserving trajectories and how they can underlie corrections to the fluctuation theorem. For the surprisal, we saw that coherences in the initial state, which are only possible because of non-commutation, can actually make entropy production negative, which is very surprising when you just start with 2 thermal states interacting. And for the third definition, we saw that the entropy production can have an imaginary component, and in fact, this signals contextuality, a very rigorous form of non-classicality. So some of the future work we're interested in is studying potentially symmetrizing some of our definitions with these quasi-probabilities, as well as seeing if there's applications now of these definitions we propose, perhaps in the designing or improving the efficiency of quantum devices. So for example, studying how a quantum heat engine could be enhanced using, say, coherences. Okay, so with that, thank you for your time, and I'm happy to take questions. Yeah.
Might be a simple, it might be a simple question, but just on this previous slide, why would the why would the geometric phases or the areas enclosed by doing like the forward and the reverse processes end up being different? Or is there like an example of a process that might give that?
Yeah. So I guess, so in general, why would they be different? Basically, there's 2 things going on. One is that you could potentially get different measurement outcomes on your reverse, like your forward process. And also that the evolution that's being done isn't like U, but U daggers, sort of driving the system backwards. And in general, you could get it. Okay. So I can show you, for example, one plot. So this is exactly this, like, okay, so what is this example? 2 qubits, and the quantities being exchanged are like the XYZ Pauli operators. It turns out that the only interaction that actually transports all 3 of those, but doesn't create or destroy them, is basically a linear combination of identity plus swap. So it's kind of like all or nothing, some like weighted combination of all or nothing transport. So we obviously have like an inverse temperature. There's like 6 of them. So for system A, XYZ, system B, the same. So with all of those other parameters fixed to some, some values, here we just look at changing the initial state by changing these inverse temperatures. And this is the plot of the imaginary component. So you can see there's sort of one contour along which is just exactly 0. But basically by tweaking the coherences in the initial state, we can either get it to be positive or negative. And so it kind of varies in a way. Yeah. And what's interesting is sort of the magnitude of this imaginary component is similar to the magnitude of the real component. Okay. So it's kind of a robust effect. It's not like something that's, many orders of magnitude smaller.
Okay, thanks.
Okay, so I have a question. So we said in the second case, initial coherences can render negative, render the entropy production negative. But we start with thermal states, right? So how do they have coherences? if I remember correctly, thermal
Yeah.
states are just diagonal states with no coherence terms.
Yeah, it's a great question. So basically our initial states looked something like this. Or actually, since I've already talked about this qubit example, maybe I'll write something simple down. So we think about a state like this of normalization. Sigma x and sigma y don't commute. So this state is actually not going to be diagonal in either sigma x or sigma y.
Okay, I see. So our observable is in a different basis than the Hamiltonian.
Yes, exactly. And until like one of these coefficients really dominates, this state's going to have large coherences in either basis.
Okay, thank you. So, any other questions? If not, let's thank our speaker once again.